Okay, so maybe we can start.
Yes.
Yes, okay, so please, Pierre, go ahead.
Thank you. Okay, so thanks, Sasha, for the invitation. I'm really happy to be here and talk about this topic. So this is really not about Kolmogorov complexity, but it is about memory in games. And this also has a taste of information. So it's the whole question is, when we play a certain game, how much memory do we need to win this game, right? But I'm going to define everything. So this talk is meant for non-experts. I want to introduce the topic and then talk about some new techniques. So what are the main open questions, in my opinion, and a new technique to make progress on these questions. Okay, so first
also, I don't care if you explain some old techniques and prove something using old techniques. Probably most of us are not familiar with any.
Yes, but so I'm really going to talk about the new technique because it's a way to re-understand the old techniques. Okay, so it's more efficient this way.
Yeah. Just prove anything with new technique is perfect.
Yes. Okay, so I'm going to start by introducing everything and looking at a wide range of examples. Then I will do a kind of landscape overview of the state of the art and so on. And then we'll go into the new technique, which is about graph decompositions, or you could also say, I like to, this is the same thing, graph decomposition or universal graphs in this setting. Okay. Also, please, of course, don't hesitate to interrupt. We have plenty of time, so let's go.
We don't hesitate, so don't worry about that.
Sure. Okay, so let's actually start on an example. So we have a set of colors here, NAB, and we're looking at a graph. And the vertices in the graph are partitioned into those that belong to Eve and those that belong to Adam. These are our two players. We always take the point of view of Eve. So Eve is, we want Eve to win and Adam is the opponent. And we have an objective. So an objective is a set of infinite sequences of colors, okay? In this case, we're looking at the objective, which is a singleton. It's just one infinite word, and the infinite word is AB, AB, AB. Okay, this is a omega expression. It doesn't really matter if you know how to read these or not, but they're quite explicit, I think. And this objective just specifies that the game should alternate between A and B forever. Okay. So that's the setting. If we're in a square, the opponent play. If we're in the circle, we play, and we choose transitions, and we want to ensure to win. So can we win in this game? Yes.
Stop now and to see what people are thinking. So let someone who didn't see this game before just try to argue about this.
I think that we can.
How do we win then? We are Eve.
We are Eve.
Yeah.
So we move. Our move is the first, right?
No. The first move.
So we start here.
So sorry. If Adam plays to the left, then we are in good shape because then we can. We have infinitely many moves in turn, and we can alternate between A and B, right?
Yeah, so there are two edges, which are one is B and the other is A.
Otherwise, otherwise Adam plays to the bottom, right? And then, then it's Adam turn again. If he plays again up, then we are again, so to say, in the same position. And if he plays left, then we are in good shape again.
And it's important that we are in the left vertex with the correct prefix. We have AB.
Mm-hmm.
Yeah.
Right.
Oh, no, we can, yeah, yes. So we can bevel with A or with AB, that's the same, yeah.
Yes. Yeah, so to rephrase it, first the opponent can choose to alternate, and then at some point the opponent can just give us the hand, and we should choose to continue the alternation as it should be, right? And this way we can ensure to win.
Yeah, what I don't understand, so there are blue and red, and there are A and B. And this is just the two ways to show the same thing.
It's just some redundancy for readability. It's not.
Yeah. So we just need to alternate the colors. Okay.
Yes. Okay. So we can win, but so there's the question of how to formalize that we can win, right? How do we win? And this is via the notion of a strategy. And I'm proposing, so there's several ways to really formalize it. I like to formalize strategies as graphs, because I like to talk about graphs, and it will appear in what follows. So here is what I would call a strategy in this game. So it's a graph that actually comes with a morphism. Okay, so here's the morphism. I'll remove it for readability. So you have a graph and a map from right to left.
So it's a strategy for whom? For Adam or for Eve?
Sorry?
This is a strategy for whom? For Eve.
For Eve, yeah.
Yeah.
So in the next slide, I will have the real definition, right? But here I just want to give intuition what's happening. Okay. So this graph specifies the strategy. So it says that we have here two states of the strategy that corresponds to these two states in the game. And then on the left, two other states of strategy that correspond to this state in the game. Okay. So a state, we have a morphism from the strategy to the game. So a state in the strategy always corresponds to a state in the game. Okay. But we are able, when we want to come up with a strategy, we are able to somehow duplicate some states of the game in order to make different moves in different states of the strategy. So this is exactly what's happening here. So we don't need extra memory for Adam states, so we don't have to duplicate them. And then, yes, Sasha, you have a question?
No, I mean, I just wanted, so there is exactly one outgoing edge in the graph on the right or not? I don't see it. No.
No, for instance, here.
The edge seems to be exactly the same, no? Or not? No.
Not exactly.
It's not the same, yeah.
Yes. So the point is that from this memory state, we play with B, and from this one, we play with A. Okay.
Yeah, depending on how the game came into the stage, we need to use different things.
Exactly. So there will be a formal definition on the next slide, but the important requirement so in the definition of a strategy is that if a state corresponds to an Adam vertex in the game, then we should have a response to every outgoing edge. Yeah. So here, for instance, we have this state is mapped to Adam state, and we have two outgoing edges with A. And in the strategy, there should be two edges that mimic these two opponent moves. Yeah. So the strategy should be ready to answer any move from the opponent, and then from a vertex that belongs to Eve, we can choose any move. Okay.
Yeah. So let me check that I understand things correctly. So
yes.
One can assume that there is an observer with finite memory who looks just how the game goes. So this observer can tolerate any move and just have some additional information. So each state has several copies, which are now mapped into the previous one copy. Yeah.
Yes.
And then observer is just observer, but the strategy adds some instructions what to do in the vertices which are ours.
Exactly.
And for all other vertices, we can keep information about other vertices if at other edges, but one edge should be selected. And in your picture, there are no unnecessary edges, just the one which we select. Yeah. And this is just a standard idea of a strategy with finite memory, just explained in a different way. With no, it is not nothing new in terms of
exactly
of the strategy.
Just we're gonna do plenty of examples to get a feel of how you work with these.
Okay,
but,
so any questions about these examples, especially from students, if which may be afraid to ask something? Don't be afraid. It's very simple. Just if it's not clear, you should just explain something is missing. Yeah, Georgi, you wanted to say something? Just say.
Oh no, I wanted to say that everything's clear.
Ah, yeah, that's also a good idea. Yeah, to say that.
Perfect. Okay, good. So I'll go on.
Yeah.
So this is my strategy, and I'm claiming that it's a winning strategy. What does it mean that it's winning? Well, now this is just a graph. So I have just one kind of vertex that I can think is a kind of an opponent vertex. So there's just one kind of vertex, and the fact that the strategy is winning means that every infinite path from the initial vertex in this strategy satisfies the objective. Okay. So here, if I take an infinite walk on this graph and I look at its color, then it's going to be belong to the objective. So this is what it means to be winning.
Yeah, it seems to be clear.
Yeah. And the memory of this strategy is 2. Why? Because I have a preimage here, the preimage of this Eve vertex. I have a preimage of size 2. So if you look at somehow locally, the amount of information that I need to store is 2.
No, so the amount of information is 1 bit, but just 2 cases.
Yeah,
so you
2 cases.
measure in not in logarithmic scale, but
Yes,
in natural scale. Okay.
Yeah. That's, I'm more used to this, but you could.
Okay. Just.
Yeah. Okay, so that's, and we're going to now play around with this. But first, let me just give a formal definition. So a game is a directed graph with there's some.
Sasha, I guess you create some noise because there is green near your thing.
Thanks.
Yeah.
So a game is a directed graph with labels on the edges. So the labels come from a certain specified set C of colors. And C is possibly infinite. There's no assumption. Also, the graph is possibly infinite. It's actually quite important that we consider infinite game graphs. And in the game, we also specify an objective, which is a set of infinite sequences of colors. We specify a vertex partition between Eve and Adam and an initial vertex. And we will always assume that every graph that we consider in this talk don't have any sink. So you can make all of this work while allowing sinks, but it's just simpler to just assume that there's no sink appearing anywhere. Okay, why no sink? Because I want the play to go on forever. So from every vertex, there should be an outgoing edge, at least one. Okay, so that's a game, just as in the previous slide. And now a strategy is, again, a graph. So again, let edge label directed and no sink. This will always be the case. It's a graph that comes with a morphism to the game. Okay. What's a morphism? A morphism is a map that preserves all the edges. So whenever there's an edge in the strategy, it projects to an edge in the game. So it's a map from the vertex set of the strategies to the vertex set of the game that preserves the edges. So every edge in the strategy corresponds to an edge in the game. And we have an initial vertex. So the strategy is, again, possibly infinite. It's quite important that it's possibly infinite. It has no sink. Obviously, the initial vertex in the strategy should map to the initial vertex in the game. And the important requirement is this one. So I already mentioned it. Whenever you have an opponent vertex and an outgoing edge, and a strategy vertex that maps to this one, that corresponds to this opponent vertex, then there should be a move corresponding to this edge. So there should be an outgoing edge with the same color that goes to some S prime, which projects on V prime. Okay, that's the definition. Okay, so intuitively, this means that a strategy should be prepared to answer to any opponent move. Okay.
Yeah, so you define strategy for if, but also you can in the same way define strategies for Adam.
Yes.
And it seems that you can have the same thing for if you don't have requirement of finite memory, then just the general notion of strategy, you can keep the entire history of the game.
Exactly.
And then, for example, there is this Martin theorem saying that for every Borel H, not HW. Yeah, Sasha, there are again some noise. Strangely.
I think I can mute him. I'm the host.
Okay. Oh, okay. Everyone is the host or just you?
No, just me, I think.
Why?
Or maybe I'm co-host.
Okay. No, that's a good thing, but it's the spontaneous violation of symmetry. So it's okay. So if we just our strategy remembers all the game, then each vertex will be just a path in the original graph.
Exactly.
And so this covers both general notion of strategy in the game and this strange Martin determinacy theorem.
Yes.
Once I even gave a talk on the seminar trying to prove it, and even somehow succeeded. But still,
wow.
I don't understand how it works. Okay. Yeah.
Okay.
Yeah.
Ah, okay.
Maybe.
Okay, good. So that's a strategy. The strategy is winning if all the paths from the initial vertex satisfy the objective. Yeah, so again, let me stress this again. This is the objective for Eve. So when we play a game, the opponent, his objective is the complement of W, right? But we will really specifically be interested in Eve and not Adam. That's the difference with the Martin's theorem, for instance, that considers both players somehow. Here we're more interested in the memory for Eve, regardless of the memory of Adam. Okay.
Yeah, it's quite possible that the winning strategies need to have different memories. So,
yes, and we will see plenty of examples of this.
Okay.
And now the memory of a strategy, let's say it's an upper bound on the cardinalities of the preimages of the morphism, right? So for each vertex, we have a number of strategy states that correspond to it, and the memory corresponds to how many we really need, right? And I'm saying upper bound for a reason that will appear that we may be interested in saying we have finite memory, though unbounded. If all of these are finite, this will appear in an example later, but you can think of just as being the maximal size of pi minus 1, okay?
Yeah,
We're not...
if the memory is 1, it's called positional strategy.
Yes, there's a slide about this.
Okay.
Okay. Is it clear? Any questions? It's important that this is clear for everyone.
Just since you all once Georgi, what do you think? Is everything clear or?
So since there was recently a talk by Sasha Shen about this, maybe it's
no,
good.
No. First, it was not recently. Second, it didn't have any success, and third, people are new, so don't rely on anything. Yeah,
but it's probably the same definition that you used, but maybe slightly disguised.
Yeah. The notion of game is more or less just if you don't care about position strategies. You just positional strategies. You just consider that the tree, and so it's kind of maximal
exactly.
Graph. But
yes. Okay, let's do some other examples. So here's a simple one. So how does the game go? First, we start here. Then the opponent can choose a number between 1 and 4, and then we can answer a number between 1 and 4. Okay, and then we start again. And the objective is this expression that means that we should always repeat. Okay, this is a set of sequences where every odd position is followed by an even position that has the same label. Okay, that's our language of infinite sequences. Okay, so what this objective specifies is that the game should every round, in each round there should be a repetition.
Yeah, I think at that point even I understand that he wins by just saying the same thing
Exactly.
to Adam. Yeah. Yeah,
Exactly.
but also that you just draw one edge, but for labels, but theoretically there are 4 edges.
Yes,
So,
sure. So
kind
this
of,
is kind of as in automata theory, I guess.
yeah.
So we win, as you pointed out, and this is how I would draw the strategy. So you need 4 different states of memory because you need to act differently according to what the opponent told you. And so if the opponent says 1, then you should answer 1. If the opponent says 2, you should answer 2, and so on. Okay. So it does meet the requirement that for our opponent state, for each outgoing edge, so there are 4 outgoing edges, well, it is handled in the strategy, right? For each opponent edge, there is a corresponding one in the strategy. Okay.
But for example, in the same game, if W consists of all aperiodic sequences, then Eve can win, but not with finite memory, yeah?
I think she can, yeah, not with finite memory. Yeah, sure. Yeah, definitely. Yeah. Actually, it's going to be roughly the example just below. So this is a winning strategy because every path in there belongs to the objective and it has memory 4. Okay, here's another one kind of similar to what you said. So Eve can choose in each round a digit, and we win if, well, we choose the digits of pi. Here's the strategy. Here's a typo that I forgot to correct. So this should be a 1, and this is supposed to be the digits of pi. So we win, right? The strategy is just, well, I'm going to pick the right digits again and again. So this is a graph that satisfies the objective. So it's a winning strategy. So this is the initial vertex. So the only path from the initial vertex does belong to the objective. So it's indeed a winning strategy. But the memory is big, right? This is the pre-image of our only vertex, and it has size countable. So we have countable memory space.
And if pi were periodic, then we could have finite memory.
Well, did we collaborate on making this? Right?
No, I just try to convince something else participate in this discussion.
Yes. Yes. So this is exactly what I wrote here, that if pi were rational, then you would have a finite memory strategy because you could have a kind of a loop, a lasso strategy, and you would have finite memory, as you said. Good. Another example. So this is kind of more an example people care about. It's called a parity game. So the colors are integers from 1 to d, and this is the objective. So it's the set of sequences such that the largest color that appears infinitely often is even. Okay, that's a parity. It's called a parity objective. So again, we win if the largest integer integers are called priorities in this case. So we win if the largest priority that appears infinitely often is even. Okay, so that's the rule of the game. So let's look at this game here. So we start there. And let's assume for a second that we choose to go to the right. Yeah, then the opponent can choose to go up and would always choose to go up. And then whatever we do, we can either an infinite number of times go down there, but then we would see 3 infinitely often, which is bad because it's odd. Or we could choose to eventually stay in this loop, but then the 1 would kill us also because it's odd. Okay, so if we go to the right, then we will lose because the opponent will just stick the game in there, and then this is a loss. right? I hope this was convincing enough. Now, otherwise, we can choose to move to the left by choosing this edge, and maybe choose to go up with this edge.
But
And
if we
this
just
is
go
much better.
cycle, it's not good. We can stop here, but this is not good for us. So at some point we need to go up.
Exactly. So let's say we go up, and then the opponent can either go down there, but then if he always does this, then we would have this nice cycle, or he can choose to go there, but this is also fine because this 3 is beaten by the 4 here. Yeah. So I'm claiming that if we go left and up all the time, then we will actually win. Yeah, because only 2 cycles are possible and both are good. Right. So in other words, this where I picked this edge here and this edge here is a winning strategy. Okay, which means that all the paths in there satisfy the objective. Any infinite path in this graph is such that the largest number that appears infinitely often is even. So this strategy is winning. Yes, Sasha?
So just a subgraph in our case, right?
So it's
Some
just
vertices disappear, but this seems okay. We don't require it because they are unreachable if we follow only the edges.
Exactly one. So it's like, so we just fixed where we go, right?
Exactly. So this is a strategy. I mean, it matches. It comes with a morphism, which is obvious, and it matches the requirements that from this Adam. Whenever I have something that projects to an Adam vertex, so this guy, and an outgoing edge, then there is a corresponding edge, right? So it matches the definition. So it's a strategy, and it's winning, and it has memory 1. So memory 1 means that the morphism is injective, right? The pre-images have size 1. And this is just the same as saying that the strategy is actually a subgraph. Yeah, it injects in the graph. And this is a very important case where the strategies have memory 1, and it's the same as saying that the strategy is a subgraph. And this is called a positional strategy or memoryless strategies. Yeah, and there's a very important result about these games, parity games, is that they are positional. So even if the game graph was infinite, it would still be true that if you can win, then you can win with a positional strategy. Okay, so I'm just going to repeat this. So whenever you're playing a parity game, so a game specified by this objective, even if the graph is infinite, if you can win, then you can win by playing always the same thing. You can win with no memory. So here, always the same thing means always to the left from this point and always upwards from this point. And this is exactly the same as saying that you can win with a strategy which is a subgraph. And this is called a positional strategy. It has no memory. You don't need to remember anything. You can always play the same thing from a given point.
Yeah, so for finite graphs, it's just this positional thing is an important part of showing that there's deciding these games is a classical thing in P and co P in the same time, and still doesn't known to be in P.
Yes, so it's coming up. It's in a.
We heard some talk about this finite games. But even probably several times, and at that time the proof was somehow understandable, but still there is some miracle, and I don't. Does anyone remembers the proof? Knows it now.
Yes, I mean I do. No, I think a few people do, but.
No, just in the world, I guess there is a lot of people. Just among the participants, is there someone else except for the speaker?
Which proof do you mean?
Anyone, any proof. Just that the game.
Any, yes. I do.
And Sasha probably also does, yeah.
I know, but I think it would be like hard to explain, Just
okay, it's a passive memory. Yeah.
So I think the most simple proof. So there will be a proof from what we will see in this talk, but
Yeah.
I think specifically for parity games, for positionality, at least for finite games,
Yeah.
it also adapts to infinite. I think the simplest proof is the algorithmic one. So the Zielonka algorithm. I think this is the easiest to understand.
And also there are first, there is some connection, deep connection with two things, with the result about three automata and the negation Rabin theorem on this. And
yes, I will also discuss this, but you're
yeah. And also there is something which is called kind of mu calculus or some completely strange thing which I never can even understand what kind of connection it is, but it seems that it's connected to something like this.
It seems.
Yeah, yes. But do you know what this strange thing is?
Yes, I will explain. I mean, I will not explain new calculus, but I will mention it on the landscape slide.
Okay.
But let me first go on with further examples. So this is another one. It always comes right after parity games. It's mean-payoff games. So that's a mean-payoff game. So the colors are integers that can be positive or negative, and we win if this is satisfied. So that's an awful formula. So let's rather look at the drawing. So whenever we play in the game, whenever we visit an edge, we update our strategy profile, which is like the partial sum up to now, right? So we add or subtract the weight, and this draws a curve like this. And what we care about is what happens in the long run. So in this case, in this curve, in the long run, so you should think about plays that are cycling. That's kind of the important case. So in this case, in the long run, it's rather going down. Yeah. So we win. I like to think as ourselves as, I mean, ourself is Eve. Eve is, I like to think of her as the minimizer. So we win if in the long run, we go rather negative. Yeah. So intuitively, what we aim to do is to stick the game in some negative cycles. Okay, that's the goal. Yeah, there's a lim soup here. Doesn't really matter that it's lim soup. It could be lim-inf. It would not change anything for finite games. But it's just so that this is defined in general. So it's kind of a
you mean that if you replace lim soup by lim-inf, keeping the edge, the weights, yes, the winner is the same.
Yes, exactly.
Yeah. No, it probably, but if it has positional strategies,
it follows. Yeah.
Then it's not surprising indeed.
Yes. And yeah, the point is going to be that we have positional strategies, but let's look at this example specifically. So let's look at this part on the right. I hope you can still see my cursor.
Yeah.
So if we're here, that's the opponent. The opponent wants to maximize. So, and he wants to be positive. So if he actually goes there, then he will always stick the game in this rightmost component. And then whatever we do, the average weight is going to be positive. Okay, so we lose. Yeah, so we really don't want to go there, because if we go there, then the opponent would just do this and we would lose.
Where do you start if you got edge?
We start here.
Yeah.
So then if we're here, then we definitely don't want to go down there. So we should rather go there. So from here, we don't have a choice. We should always go there. Now the opponent here can choose to go here and there, right? Since we would always go there, but this is fine because this is a negative cycle. So we're not afraid of this. And also the opponent could go there. And from here, well, if we choose to go back there, then this actually looks pretty bad, because then this would be a positive cycle. So this would be losing. Yeah, so from here, we have two choices. I mean, we can go to the right or to the left. To the right is also bad, because then we would cycle like this. And this is, again, a positive cycle. So this is pretty bad. But if we go to the left, then we're fine. Yeah, because here there's the two possibilities are only negative cycles. Yeah. So if we put all of this together, we see that we win. And the strategy is this: from this place, we would always go down. And from this place, we would always go left. And this is our strategy. And since it's a positional strategy, it's a subgraph. I'm just writing it as a subgraph. Yeah, I'm not writing it separately as before.
So
Just
in your
highlighting
explanation, it sounds like analysis is something more or less, so to say, linear, but this is just an illusion, probably.
Yeah, this is an illusion. I thought from my explanation, it sounded like this seemed like hard, but yeah, it's definitely
No,
not
you just
linear.
go from one part to other, and then you can
Yes.
reason about them and blah blah blah, and you're
Yeah, that's true. That's true.
But
Yeah.
but it's just an illusion, because if something is more complicated, then it's not clear what to do.
Exactly. So this is a winning positional strategy. All the cycles in there are negative, which is the same as saying that all the paths are negative in average. And the point is that these games, the finite ones, they are also positional. So this is an important theorem, which was proved a few times. But this, I think, is the first proof. Yeah, so that's it about mean-payoff games.
Okay, so that's good time to ask. So is it clear what is a mean payoff game, and why the specific game has the specific winning strategy? Just
you mean this concrete graph, or
yeah. This concrete graph and this concrete strategy for the graph. Is it clear, the explanations?
Okay, but we should just check in that case. So we have this green subgraph, right? And we just have to check that all cycles are negative there, right? Just to verify that this strategy is winning. Yeah, and that should be clear, right?
Yeah, no, okay. I don't doubt that it's clear for you, but just let other people say that this is clear for them.
I agree that it's clear.
Yeah, great. Okay, but also how it's related to parity game. I remember that someone explained me that one is reducible to other.
Yes. So
which is reducible to which?
Mean-payoff games are more general, harder.
And how do you reduce them?
So if you have a parity game, let's go back to the previous slide.
Yeah.
Parity game. So this is my parity game. If I want to reduce it to a mean-payoff game, so only finite ones, right? The point is, we know it's a consequence of a positionality for both game. So
yeah.
if I look at the size of the game, so this is a size 5 number of vertices, then I would replace my odd prior. I would replace. So let's say 5 is n, right? Size of the game is n. I would replace an edge with priority p by an edge with priority minus n to the p. Okay, so for instance, or no, sorry, minus this. Okay, so it's a bit confusing, but this 1 would become 5. Yeah, and the 2 would become minus 25, and the 3 would become plus 125, and the 4 would become minus
So
5 to the 4, right?
To make even things are positive now and odd are negative. And
yeah, I'm doing the inverse. So Eve is minimizer, so even should be negative.
Yeah, even should be negative.
Yes,
it's positive, and they should increase. So somehow the maximum in lim sup is reflected by the fact that the maximal is more important than all the sum of all smaller things below.
Exactly, and this works because if you think about it, what matters is really the cycles, because when you fix 2 positional strategies, so one for Eve, one for Adam, then the path that you will follow is just points to a cycle, right? and who wins just depend on the weight of the cycle. So the only thing that matters
this is cheating. So what I want to understand, whether we can prove that parity games are positional using the
no,
same
this we
result
cannot.
for mean payoff, because it's strange, because it's 90 and the other is 79. So
I think
yes, no. So positionality, no. If you assume positionality, then you can reduce parity games to
so the danger is that there is some path when large even numbers, large odd numbers appear infinitely often, but rather rarely. So they are influence the limb super.
I think we can. There's no problem, because you consider the mean payoff game with large
No, I don't think you can, Sasha, because you have to, for this to be true, you have to, I mean, the games are positional, are equivalent in a weak sense that they have the same winning positional strategies.
Okay, let's Sasha make an error, and then you will explain this error. So
yeah,
Sasha,
I mean,
please.
Sorry.
I mean, you have let's say you have a winning positional strategy in the mean payoff game.
Yes.
So
the weights are just as explained. Large
large gaps, alternating negative. So that if I consider just simple cycles, then negative cycles corresponds to even. Right?
Yes.
Then we have a positional strategy from proportionality of mean and payoff games, which guarantees that all simple cycles are, or I don't know, yes, negative. And in terms of parity games, it means that this strategy guarantees you that all simple cycles are even. And from that, you can really, it's easy to deduce that this strategy is winning against any, not only positional strategies, but because if you have any infinite path, then it will have a cycle, and then this cycle can be decomposed in, you know.
But it's
I agree.
What do you mean? What is more exactly this decomposition argument? So you have a graph.
The thing is, if I have a strategy where all cycles are even, then this is the winning strategy.
So just why you consider arbitrary path?
Yeah, which presumably fails this strategy.
Yeah.
So starting from some point, there will be some
large odd number, maximal odd number,
which appears infinitely often, and all the other guys that appear infinitely often will be smaller. Then you look just at the occurrences of this large infinite odd number, the largest one. There will be 2 times when it visits this, where it happens in the same node, and you get a cycle where the maximum is this large odd number. So it's
so you can use this cycle to get this.
Yeah, and then it's not simple, but you can present it as some union of simple cycles. And one of them.
Who is not simple, the cycle or the argument?
No, the cycle. I mean,
no. I thought that there is some hidden difficulty there.
No, so that's all.
Okay, and then how do you explain that this is you need 11 more years to prove it's for parity games?
Because this is for infinite parity games. So only finite mean payoff games are positional, but the result for parity games is stronger.
So people knew for finite parity games that they are positional before.
Yeah, I mean, they didn't really know the existence of parity games. It's also kind of
it was just
historical.
Instant. Okay, yeah.
And probably, so they didn't had a connection between these two things.
Yes.
I guess.
Yeah. Actually, the way you would, I think the simplest, I mean, there are several proofs, but maybe from scratch, the simplest proof of positionality of mean payoff game is actually by reduction to discounted games, which are even more general. I don't know if you would agree with this, Sasha, but I would say.
Okay, but this you will explain probably next time. Okay.
Yeah, no, I don't want to go into discounted games. This was just, in the end, I'm not really interested that much in this talk about parity and mean payoff games. It's more like to introduce about the field. I mean, these are.
Yeah, you are not, but we are.
Yes, exactly.
Yeah.
I mean, I am, but it's not the point of this talk.
Yeah.
Now I want to go into maybe more exotic examples. Okay, there's just a few. So this is an objective. Again, the colors are all the integers, and we want it to be bounded from above and below. So Sasha knows this objective very well, or he does or below, but or something. But okay, so we accumulate the weights, and the path that we get, we win if it's bounded from above and from below. Okay. And I want to look at specifically this game graph, which I will now describe. So initially the opponent starts and he picks one of these gadgets. Yeah, so he chooses to play forever, maybe in gadget number I. So it's an infinite graph. So there is one gadget per positive integer. So the opponent basically chooses an upper bound, I. And then we play in rounds where in each round, the opponent chooses a weight within the bound or within minus the bound and the bound. And then we can answer a weight within the bound also. Okay, that's the graph. Okay, so that's the game. So I will pause maybe and see if
so we want to be bound to this thing to be bounded.
Yes.
So it's in our interest to make that just the negative move and compensate the move of the opponent. Yeah, that's what.
Yes. Yes. So,
and there is no other choice for the opponent. He cannot leave this part of the graph.
Yes. So we win, right?
Yeah.
So just before showing it as a graph, the strategy is quite simple. It's what you said. So whenever the opponent plays weight X, then we play weight minus X, right? That's it. Yeah. So it's a simple strategy, and I can draw it like this. So in gadget number I have this kind of repeat thing where whenever he says something, then I would just answer the opposite. Okay, that's the strategy as a graph. Okay, and so this is a winning strategy. If I take a path in there, well, it kind of the profile looks like kind of a triangle thing, and it doesn't diverge. Yeah, it's bounded from above and below.
No, so this is not the only winning strategy, but it's one of them.
It's one of them. Yeah, you could choose to kind of save for later or whatever. It's one of the winning strategies. Yeah, but it is winning. But I want to mention this game because it has a special memory status, which I think is interesting. Is that the memory is finite in the sense that each pre-image is finite. However, the memory is not bounded. It's finite but unbounded memory for this specific game graph, right? So there is the pre-image of this graph has size I, and we have this for all I, right? So memory is finite but not bounded. Okay. Does that make sense?
Yeah, it seems just what people think. Is it clear, this example?
So, sorry, I did not hear what you said.
I think Kole agreed, but somebody else
okay.
Would say something probably.
Yes.
And Andre is also happy.
Okay,
Georgi, what would you say?
It's clear, but I'm not sure I understand what memory is then. Like it's an upper bound, but we don't really have
No,
any.
now the memory is for every vertex. For every vertex, we just have count the number of pre-images.
Yes.
So how many bits we need to, not how many cases we need to have when we are in this vertex. And for winning strategy, this for every vertex, this is finite, which is not generally the case. If there is a loop in a graph, we may wish to remember the entire
think
history.
Jorge's point is that here the word memory, it's not clear if it's a number, if it's, so it's a bit informal here. This is what I mean. It's not a soup of the size of the pre-images, otherwise it would be bigger than this, right?
But so let's try to understand.
Yes, it's finite. Yeah.
Is it possible to win this game with finite memory? Probably not, but why? Can we see why this game is not winnable with finite memory, with bounded memory? So imagine we need we have some upper bound and cannot distinguish between more than 1,000 cases. Why we are doomed to fail?
Yes.
Can somebody
requires an argument? Pigeonhole. I don't know. I mean, we would need to think about it, but I want to go on.
Pigeonhole. So if there are several things, when we do the same, depending on with different things.
Yeah.
So and then we consider the strategies which do one thing and other thing, and one of them will lead to infinite. Thing.
I think so a way you could argue, just look at take a big eye and look at just the image, the size of the pre-image of just the gadget eye. Yeah, this is a graph. It can behave in different ways. And now, but since I is very big, and since you have a bound on its size, which is like twice the memory and which is bounded, then there should be two x's, two weights that have exactly the same edges in this graph, yet both paths should be bounded. So this is not possible.
Yeah, but it's a bit more complicated because the square vertex can also have several pre-images.
Yes, but I'm saying there are two edges that have exactly the same behavior inside this graph of size 2m.
Yeah.
And then I can take two parallel paths and then I can pump it. I mean, it has to be an edge that belongs to a cycle, but that's okay. I mean, yeah, take a strongly connected component and repeat the argument. Yeah, you could argue like this.
Yeah.
Good. Okay, and why I think this example is interesting. Well, this you can see as an intersection of two objectives, which you can call bounded above and bounded below, which are quite explicit. So bounded above is the objective where I win if it's bounded from above, and bounded below is I win if it's bounded from below. This is intersection. And now these two things are positional. So these are sometimes called energy games, and they are positional over infinite graphs. However, their intersection is definitely not positional. Here we need a large memory to win. So positional objectives are not closed under intersection. Yeah, and this example also shows that this is the case for bounded memory objectives. They're not closed under intersection.
And how do you prove that bounded above is positional?
Yeah, this requires you can prove it at the end. Maybe we can prove it with the technique. I mean, with a universal graph. This is a way to prove it.
So it's simpler than for parity games, but also requires some reasoning. It's not obvious.
Yes.
Yeah, that's what you say. Okay.
So they are not closed under intersection. However, I want to mention that it's true that first, it's true that this objective has memory finite in the sense that whenever you can win the game, then you can win with this kind of memory, so finite but unbounded. I just showed it on an example, but it's true in general. And it's also true in general that if you take two bounded memory objectives and take their intersection, then you cannot go higher than this kind of memory. This is a consequence of our new results. So I think this is an interesting class.
So if you take two games which are positional,
yes,
then intersection has locally finite memory.
That's yes, exactly.
And if you
locally finite.
And if you have two things with locally finite memory, the intersection is also with locally finite memory, or
this
not?
I don't know. I conjecture that yes, but I don't have a proof. But I can prove that if I have bounded memory, like finite bounded, and do an intersection, then I'm locally finite.
But locally it means what? So on any path is bound, any infinite path is bounded.
No. Local memory, finite memory means that for every vertex of the infinite graph, we has only finitely many pre-images, but the number of pre-images is not bounded. So in every vertex, you keep only finitely many bits, but you in different vertices, this finite number of bits could be the same, different, and not bounded.
Yes, exactly. So that was one exotic example of a more advanced thing that you can look at. Another example. Okay, so this is some number occurs infinitely often. So we have countably many colors, and we win if one of them occurs infinitely often. And actually, let's look at this game where the opponent plays and does anything. Yeah. So the opponent can basically play anything. Do we win?
But the labels are infinitely many.
Yes.
No, then the opponent, of course, can just took different labels all the time.
Exactly. So we cannot win. So the opponent wins, then this means that I cannot have a winning strategy. And what I want to highlight here is that the opponent requires infinite memory to win in this game. So again, this requires an argument. A finite strategy would have a cycle, and then the cycle, well, one number would occur infinitely often, so the opponent would lose, right? So the opponent does require infinite memory.
But this is a bit unfair because there are infinitely many labels. So
yes,
it's more natural to ask about finite memory if we have finitely many labels.
Still.
No, that's all is true, but.
Still, it's true that it's positional for me. So if I can win, if I play this objective and I have a game graph where I can win, then I can win with a positional strategy. This is true. And this is a difficult proof, like surprisingly difficult to prove, I think. So if you want to try to look for a proof of this, so I put nice proof wanted. Now I think I have a proof that I'm happy with. But yeah, it's surprisingly difficult to prove actually that it's positional, but it's true. And what it tells us is that positionality or finite memory is also not closed under complement, because here we have a positional objective, but the complement or Adam, well, he requires infinite memory to win. Yeah. So what I mean.
Sorry, may I ask?
Yes.
W means is positional means that if has a positional strategy.
Yes, it means for.
But she has no moves in this game.
Yes, this is where I should have been clearer. It means what I mean here when I say W is positional, it means for every game graph where I play with objective.
Oh,
W,
I see. So the objective the same for any game graph.
Yeah, this is the entire thing, which is quite non-standard, I guess, and deserves to be understood well. So yes. we are trying to do a strange thing. We have some property, and then we apply this property to every graph.
Yes.
And this is rather strange because, for example, if we just relabel some vertices or some things, just change labeling, then the game may change very significantly.
Yes.
Still there is some kind of thing which is makes the entire thing guaranteed to be positional. And if we require it for finite graphs, and this will be the same property or different property?
Different. For instance, mean-payoff games, they are positional only on finite graphs.
Mm-hmm.
So yeah, so just to stress this, we're interested in objectives actually. So positionality, we look at it as a property of the objective where the graph is able, the game graph can vary. So positional is very strong thing. It means positional on any game graph.
Mm-hmm.
Yeah. Okay. And now I have one last maybe difficult example. This is the most difficult. So we have again countably many colors, and the objective is I win if only finitely many numbers occur infinitely often. Yeah. So it could be that there's an infinite number of elements of natural integers that appear infinitely often. For instance, if I do 0, 1, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, then each number occurs infinitely often. So there's infinitely many numbers that are going to occur infinitely often. So here we win if this does not happen. If there's only finitely many numbers that appear infinitely often, maybe there are none, then this is also finitely many, right?
Previous one is the subset of it.
Sorry?
Previous one is the subset of it.
Sorry, come again. Sasha?
Previous one is the subset of it.
Yes.
No, but
No, because previous one we would win if infinitely many appear infinitely often. So the previous one was
everyone
some number occurs.
Some number. It's for
number of element, like you could say cardinality of inf is greater than 1.
Yeah, but for Adam's side,
of inf is finite.
Yeah.
Sorry?
From the Adam's side, this is a part of
yes.
Yes. That's probably what Sasha wants to say. Yeah.
Okay.
Okay, so it's of next layer of the hierarchy. You need one more quantifier.
Yes.
Not one more, two more quantifiers.
Yes.
Infinite.
So my question is whether this is positional. Yeah.
No, we don't know even for the previous one. So, so you know, but
yeah, I know, but it's really not clear from what we've seen so far. And I think it's difficult to approach this question. And maybe is now a good time for a 5 minutes break.
No, if you want to make a 5 minutes break, it's always okay. You are always welcome.
Yes, I would want to.
Okay.
But then you can maybe think about this for 2 minutes.
No, maybe Sasha or Misha will say something, but for me there is no hope. So you can.
I'll be right back.
Without any excuse, you just make a break. Yeah. Okay.
Thank you.
Yeah. Yeah, maybe we can, Sasha, there is some strange noise. I don't understand what is happening, but it comes from the phone or something is not.
Yeah, maybe just a sound from the street. I don't know. But I close all the windows.
Yeah. No, strangely, when you say something, it's perfectly okay. Maybe there is a loop, positive feedback loop if you don't say something. So you should say something all the time, and then we will be happy.
It sounds similar to the noise that can be inducted by a cell phone, which is next to the headphone sometimes.
Also, maybe one can improve this by using this, how I say, garnitura, just the earphone and ear plug, and these things are okay.
Looking at the aspect ratio of Sasha's camera, I guess there are some issues with separating the cell phone and the connection there.
But you are even more interested. You create even more interesting noise. You make krr, 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 once in a second. How do you do this?
No idea actually, because I don't know actually. In Big Blue Button, I think it didn't happen.
Other people also hear this noise, or it's just me?
Yes, yes, we hear it.
Yeah, just very strange, very regular. Так, хрясь, 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 хрясь. Just if somebody wants to make some пилит что-то так.
Yeah. I guess in Misha's case can be some software issue.
But very interesting. We try to investigate all the noises we have, but no progress up to now. So, but meanwhile, maybe Sasha or Misha can say something about this positionality of this stage thing. Or maybe somebody else, I don't know, but just okay. So you find the question to feel all of us fools. So it's a good idea, but
yes.
Yeah.
Okay, so my point is that it's hard to attack, and my claim is that I'm going to give some tools that allow us to attack this question together, and we will come back to it at the end of the presentation. Also, I want to ask, I don't have an eye on the time. Oh, okay, so time is flowing. I don't know, is it a strict hour and a half? What should I do? Should I hurry up or?
No. The first question is unclear, but the second question has clear answer no. Don't hurry up. No, okay, good. Maybe we will ask you to continue with this or with something else, because up to now it's very clear. So it's kind of a we are interested in continuation, but so just don't hurry up.
Okay. So now I'm finished with the first part. So definition and examples, and also I introduced parity and mean-payoff games.
But we don't see this intimidating slide, but probably it's not needed.
Sorry?
No, we don't see any details on your slide, but probably.
It's not needed. Yeah, it's just a de-zoom. And now there's a zoom to another part, which will be a landscape overview. And I think this we could talk about it for like an hour, but then I have a third part. So I'm still going to...
Let's switch to, if we can go at third part without, we can just, how you prefer.
Yes. No. I mean, this is, I think it's good to talk about it now, but I cannot give a full overview of all the landscape, but I will try to be a bit maybe quick.
Yeah,
but we can also talk for like maybe 20 minutes, whatever.
Yeah.
So my point is that I think this is also, so some disclaimers. This is like my own point of view on the landscape. It's also aimed at towards the questions I'm interested in, and it's not exhaustive. Okay, but my way of seeing the things is that in this theory of infinite games played on graphs, on the computer science part of it, there's basically two different kinds of questions. There's questions that are more structural and questions that are more algorithmic. So a typical structural question is how much memory is required to play optimally. For instance, prove that parity games are positional, or prove that, I don't know, energy games are positional, or understand the memory of this or that kind of objectives, and so on. And then the other kind of question is algorithmic, which is about deciding the winner in some finite, or at least finitely presented, but let's say finite graph. Okay, these are the two types of questions. And most often, well, if you want to tackle the algorithmic question for some class of objectives, then you should first understand some structural properties like the memory, right? So this kind of structural understanding kind of precedes algorithmic understanding. And we have some here on the right, some interactions with practice, and also interactions with several other related fields. And I came up with this slide, which is a bit messy, but I hope you can read, or is it too small?
It's too.
Yeah, it's readable.
Okay, good. So let me comment on this. So this is, I think, kind of the global landscape to me. So let's see, kind of historically, I think it all started in the 60s with the work of McNaughton and then maybe with Rabin's theorem, I think, for infinite graphs. So Rabin's theorem is the decidability of MSO on the complete binary tree. And the proof of this was very difficult and kind of famously difficult. And even Rabin said that he would like it to be simplified. And this uses tree automata. And now in a tree automata, there's a way to understand tree automata as games by saying that, well, there is one player that chooses the transitions in the automaton and the other player that chooses the direction in the tree. And this leads to an idea of considering games. And this was an idea from Büchi, that maybe games can help in having a simpler proof of Rabin's theorem. And then this was successfully implemented by Gurevich and Harrington in 82. And in more recent language, what they prove in this paper, and it's a very difficult proof, is that Mueller objectives have finite memory. And of course, they show that this implies like a complementation of tree automaton, which is the hard part. This is still quite difficult. And then there was more work for simplifying this. And different lines of work, and one of these lines of work ended up considering parity games. This is I think how it came roughly. This is just very rough, but in the 90s, parity games were introduced kind of in this spirit of simplifying this proof, also with a connection to mu calculus. And then Emerson and Jutla proved that they are bipositional. So what I mean by bipositional means positional for two players. Okay, so that's one thing. And then there was more work that led to really understanding for this.
What does it mean, positional for two players?
Sorry?
What does it mean, positional for two players?
Well, positional for Eve. So if Eve can win, then she can win positionally.
Yeah, but parity games are symmetric somehow. Why? What's the difference?
Yeah, that's it. I mean, it's not stronger. It's just that.
Yeah. Okay.
Yeah. But yeah, they're like symmetric, as you said. Yeah, it's not harder to prove bipositionality than it is to prove positionality for parity. Then this was further extended to like a superclass of parity objectives, which are Mueller objectives. And people understood the exact memory. So if you give me a Mueller objective, so this is kind of a wide class of objective, I can tell you exactly how much memory it requires. So this is very
what is Mueller objective?
So a Mueller objective is an object. So you fix a finite set of colors, and you specify exactly, and you fix a family of subsets of your set of colors, and you say that you win if the occurrences that the set of occurrences that
infinitely often colors is in this list.
Exactly.
Yeah.
And these are from the point of view of memory, and this is completely understood. So this is more general than parity games, right? Parity games is a subclass. And for this, we completely understand memory from the 90s, right? So there's a kind of data structure that's called a Zielonka tree, and there's a lot of work on Mueller objectives. Okay, so that's kind of one line of research. And then there's another one which originated from another field, more like with inspiration from stochastic games.
But before you get to the second part, I still have a question. Maybe you know something. Yes. So there was a proof of Andrei Muchnik as a Rabin theorem without any transfinite induction, just a very constructive one. And
yes.
I even knew it at some point and even wrote paper for Muchnik,
Yes.
but this was long ago. But it seems that there was also so it's just the same. If you know, it's just the same proof as translation from game, or it can be go
be
another
honest,
direction.
I don't know. So this from 83, no, or some like around this time, right? 83, 84.
No, but I think it was translated to English much later. But originally it was in 80 or something like this. But no, this is not a priority question. I just want to understand. So if for example, if we know this result about Rabin theorem, can we go another direction and prove something about positionality of some games or finite memory of some games? Or
that's a good question. I never thought about it, but I don't think so. I don't think you
so
can.
Maybe this proof could be an argument translated another direction, but it doesn't go that way.
But it's not clear.
Sasha,
yeah.
Sasha, I have a I don't remember exactly, but I remember that Andrei said that Gurevich and Harrington proof is much simpler. Actually, it is much simpler than his proof.
For determinization, for negation of
yes, and it is simpler because implicitly they use Martin determinacy theorem.
And indeed you need Martin determinacy theorem for that. Imagine we don't know it, so can we still make this blue arrow?
I don't think so.
I don't know.
I think that they use Martin determinacy theory, and without it, we do not have that arrow. I mean, in Andrei's proof doesn't rely on that.
Yeah, it doesn't rely on any Martin determinacy.
Yeah. So we do have that blue arrow, but if we want to use Gurevich and Harrington, we need also Martin determinacy.
Even from finite graph, for everything is finite.
I think so.
I think for finite graphs you can,
or maybe Sasha
and Landweber.
We need Martin determinacy for some restricted class of games. Maybe for that restricted class of games, it's simpler than in general.
But I guess the starting from the third level of Borel hierarchy, it's not. It's.
But maybe the games which correspond to trees are on the second level. I don't remember.
No, if it's the second level, then Martin determinacy is just a simple argument. So it doesn't.
Okay.
It won't be something.
Maybe we need only the second level.
Okay, so this is not clear.
Yeah, I'm not sure about.
Yeah.
I mean, I never try to understand exactly this proof here. Yeah. So I don't really know. To be honest. But okay, so I was talking about mean-payoff games. So there's this proof of Ehrenfurst and Michalski about positionality of mean-payoff games. I think it's interesting that I think they didn't. It really does not come from the same place as Rabin's theorem and so on. So it's quite surprising. But anyways, since we have this bipositionality, then people realize that this implies that mean-payoff games and also parity games belong to NP intersect co-NP. And this is now on the algorithmic side. And I think this is definitely the biggest algorithmic open question, whether parity games or mean-payoff games can be solved in p-time. So more of this in a second. Also,
but this is only for finite games. So in the left-hand side, we have for any games, and
yeah. Another thing that these two results sprouted is well, people wanted to understand exactly to understand better bipositionality. So positionality for both players. So bipositionality is the thing that corresponds to NP intersect co-NP, right? And there was some work, I mean, a lot of work in the 2000s, and actually, and this was very successful. So bipositionality, so objectives such that I am positional and also the complement is positional, this is quite well understood. So for finite games, we have this result of Gimbert and Zielonka that gives a characterization, which is quite nice, and it has a very nice byproduct that people call 1-to-2 player lift. So a consequence of this characterization is that an objective is bipositional for finite game graphs, if and only if it's true for graphs that are owned only by one player.
And this is what Sasha tried to explain at some point with some success. Yeah?
Yeah, I mean, long ago, I think.
Not very long ago. Okay.
So this is super useful. For instance, you can get positionality of mean-payoff games very easily in this way. And this is, but this works for both players and only on finite arenas. So it's kind of, it's one scenario, right? Also, there's this very nice result of Kolmogorov and Nivinsky that says that if you have an objective which is bipositional on all arbitrary graphs, plus it's assumed prefix independent, then it's a parity objective up to renaming the colors. So that's a very nice result. So it says that essentially the only objective which is positional and the complement is positional and which is prefix independent, this is a parity objective. Okay, so I think with this, it's safe to say that bipositionality is quite well understood. But my point is that bipositional is kind of restrictive. It's like if you want to only look at NP intersect co-NP, but you're not even interested in NP in itself. Yeah, and I think there's still a lot of work to do for just regular positionality. Okay, now let me maybe describe more on this right side what's happening. So we have parity games and mean-payoff games. Here's a connection to mu calculus. So the point is that, so this equivalence here means p-time equivalent. So solving a parity game is p-time equivalent to model checking mu calculus, whatever this means, whatever mu calculus means. So mu calculus is, it's like a model logic that uses fixed points. But I mean, let's not really worry about it, but it gives a big motivation for also the problem of solving parity games.
But do you know what mu calculus is? It can explain at some other time, or this is something very unclear?
I mean, I know the definition, but I'm not the right person to give a survey on mu calculus.
Just to prove the equivalence. Not the full survey, just to understand something.
Can I suggest a name of someone that will do it better than me?
Oh, if you can organize this, it's very good idea. Yeah.
Yes. Okay. Okay. Well, I can try. Yeah.
Okay.
We can discuss it later. But mu calculus is important from the point of view of verification. So it's like, it's a very rich language. It's more general than LTL, CTL star, and I mean it's very expressive. But it's
if you want us to if you think that we know what it is, this ABC stars, that's not the case.
If I don't really know either.
Okay.
Say.
People say this, so why not to say this again? Yeah. Okay. Good.
No, I just mean it's not really a practical thing, but it's important because it's very expressive. And it's like more, you can express practical stuff in mu calculus. I mean, that's what I know.
That's what people say, more exactly.
Yeah. Okay. Now, so parity games are in NP intersect co-NP, mean-payoff games as well, but we still have a few algorithms. So we don't know how to solve them in p-time, but we have a few algorithms. So two important algorithms are value iteration and strategy improvement. So these are more like algorithmic ideas, and then they can be declined in different ways. But so value iteration, yeah, I don't know if it's maybe not so. I mean, this talk is really not so much about parity games, but these are like two algorithmic ideas that come from that are inspired by the same things about stochastic processes, like value iterations for MDPs. This is like from the 60s, and then they've been adapted to parity games to give algorithms. And strategy improvement is another kind of simplex kind of algorithm that can be applied to both parity games and mean payoff games. Okay, and it's interesting to see that we have also connections in the other direction.
And this recent quasi-polynomial algorithm for parity games by a group of people from New Zealand.
Yes, this is up there. I'll come to it. Yeah, let me talk a bit about strategy improvement. So strategy improvement is a funny story. So it comes from the 2000s, and it's adapted from stochastic games. And when people kind of realized that you can apply these to parity games, they were super excited, because in practice it runs in like very, very few iterations, less than 10 iterations, even on very big games. So people were super excited. They thought that they had found a polynomial time algorithm for parity games. So there's even papers where people claim that parity games are p-time. We just don't have the proof, but it's p-time, and so it's kind of funny. And then in 2009, Friedman came up with a lower bound for strategy improvement that states that actually this algorithm cannot run does not run in p-time in general. So this was a big breakthrough, and it's a complicated construction. It's a difficult one, and then this was again declined in many different ways to get some exponential lower bounds for simplex pivoting rules in linear optimization. So this is kind of an outcome of parity games, actually, which is quite surprising. So the point is, you have this strategy improvement algorithm, which is kind of simplex states. There's a pivoting between positional strategies. Then there's this parity game that gives an exponential lower bound. And then people realize that you can take this parity game and turn the opponent into a random state. So then you take this game, this two-player game, you turn it into an MDP, so a player against randomness, and still it's going to be a hard example. And now this gives, using exactly this, you can get for some pivoting rules that for which we did not have lower bounds, you get exponential lower bounds, and like important rules. I don't remember the name of the rules, but like very natural ones. So there's a whole line of work that adapts this example to get other lower bounds in optimization. So this is quite nice. Okay, and another thing about strategy improvement is that you can also take some things from linear optimization, for instance, pivoting rules that give like this random facet pivoting rule that gives you randomized sub-exponential runtime, and you can make them work on strategy improvement. So this was done by Björklund and Vorobyov, and this gives a random sub-exponential time algorithm for mean payoff games. Okay, so we do have sub-exponential algorithm, but randomized. And this is a big open question whether we can do deterministic sub-exponential for mean payoff games. This we don't know. Okay, and I should have mentioned that we also have pseudo-polynomial time algorithms for mean payoff games. This is quite simple. This, like the simple algorithms, I mean the most simple algorithms, for instance, value iteration algorithm for a mean payoff game, this runs in pseudo-polynomial time. So if you write the weights in unary, this is p-time. Good. What else? Okay, so interactions with practice. So there's this whole thing of reactive synthesis that a lot of people also talk about. So the principle in reactive synthesis is that you have a system, you have some inputs and outputs, and it's a reactive system. So this means that it's not like a program where the algorithm stops and gives an output. It's more like there's some inputs, and at some times you can your system will have some outputs, and it goes on for infinitely long, and you want to satisfy some specification, right? So it's a real practical scenario, like hardware stuff or embedded controllers, where you have some input and some output, and you have a specification on what it should look like. And the goal of synthesis in this scenario is that you get the specification from a certain logic, and the goal is to automatically synthesize a system, like a finite state system that would meet the specification. And well, depending on the logic in which the specification is written in, you get different questions. But for instance, the most used logics, such as LTL or even MSO, then you can turn this into a parity game. I mean, MSO, not really, but okay, let's say. So reactive, so games are mostly used in practice, these games, to tackle this reactive synthesis question. So that's, I think, the main interaction with practice, and it's pretty big field. And this gives a real interest in solving parity games in practice. Okay. Okay. Bounded. Okay. So sparse parity games. So we have, or like parameterized complexity of parity games. There's quite a few things that are known as well for parity games specifically. For instance, parity games of bounded click width, which is much more general than bounded tree width. These guys can be solved in p time, so this is known. However, mean-payoff games, there's almost nothing is known. So there's some very, very recent work, but still we don't know how to solve a mean-payoff game of bounded tree width efficiently. This is open. Okay, so that's for sparse stuff. And now quasi-polynomial stuff. Well, there's been this recent breakthrough in 2017 that parity games can be solved in quasi-polynomial time, so roughly n to the log n. And then this was redigested and re-understood, and now people talk about universal trees. So this quasi-polynomial time algorithm, you can see it as actually a value iteration algorithm, but enhanced with some additional data structure, which is quasi-polynomial, and this is called a universal tree. And now the bad news is that any universal tree that you would require for running this algorithm has to be quasi-polynomial. So it cannot be that this idea of value iteration yields something better than quasi-polynomial. So this is what happened in the recent years about parity games. Okay. Now you can wake up if you fell asleep. I'm going back
we yes. Admire your nice advertisement. How to say it? Intermission. Yeah. So don't expect we understand any of these many letters you told us.
Yes.
But no, maybe indeed it's a good time to stop for today, and then next time we start with explaining some proof of something or some technique or some tools and so on.
Okay, I'd be happy to do this.
Yeah, and also if you don't need to prepare any slides. It's even better if you can write. Do you have the board to write or not?
Yes, I do.
Yeah,
I mean, I can, here I have this, but I can set it up so that I have it on my iPad, and it will be easier for me.
Yeah. So if it's possible, this will be easier, I guess, both for you and because in this way you can like you can go only back and forth, and then you will be completely unleashed and can talk on what you want without any restriction.
Yes. Okay, so I think for next time, I can maybe finish the slides in half an hour. and then show you and then prove whatever you want that to see proved. Yeah.
But
I mean, the
maybe-
slides, there's no proof. It's completely informal until the end.
Maybe it's better to start with the proof and then, because we are now we are in the conference mode. We heard a lot of
Yes.
things, and we will forget it anyway. So if we just try to switch to under,
Yeah, but I think
mode,
before proving, so the rest of the slide like explains the result, and then I can prove it after explaining it, right? I mean,
okay, just do what you want, but the idea that maybe you prove something maximally simple, maximally simple case, not you. So you don't need to advertise your great achievements. Just to we believe you. So just explain something which we could really understand.
Yes.
Were it your result or not your result, don't worry about this.
Yes.
Just explain something in maximal details, and maybe also Sasha Kazachinsky has some special requests, but that's up discuss with him. And,
yes.
And hopefully Misha will make a file recording and put it on the web page.
Yes, so the next time is a continuation of Pierre's talk. Anyway.
Yeah,
so,
next time, just exactly in a week.
Okay.
Yes, the same time.
Yeah.
All right.
Okay.
Okay, cool. So let's do this. So thanks for being such a good
audience. Yeah. You don't don't rely on this. Okay.
Okay, so see you next week.
Next time.
Yeah.
Bye.
Bye.